Okay, let's get started. Before going to the next instruction, that is restart instruction in branching operation, let's do this example. This question is about what will the stack pointer value at the at the last of the execution of this instruction, that is return. Okay, so 1000H contains LXI SP2719S, 1003 contains call 3000S, so calling the subroutine at the address 3000S. Okay, so before calling 1006, the address of the next instruction will be stored in the stack. Okay, so here, see here, stack pointer value is 2719H. Stack pointer value is 2719S. Okay, and 1006 is stored in the stack, then it will decrease by 2, and stack pointer value will be 2717. Okay, decrease by 2. Come to next instruction. Now it has called 3000 subroutine from the address location 3000H. See here, 3000H contains LXI H1919H. H is by default HL. Okay, so H will contain 19, L will contain 19. Next instruction is push B. There is nothing given uh, in the B and C, but just push the content. Assume that there is a content in the B and C. So push B operation will store first B and then C. Again, stack pointer value will decrease by 2. Okay, now push H. What was the content of HL? 1919H. So again, push H, stack pointer value will decrease by 2 after storing 1919. What is the 1919? Content of the HL pair. Okay, okay, so we finished up to here. No, we need to store PSW also in the stack. Okay, so again, storing PSW. What is the PSW? PSW is AF. So again, stack pointer value will decrease by 2 after storing A and F. Okay, AF is PSW value. PSW program status word is nothing but AF. Okay, now LXISP 3C82H. Now stack pointer value is updated 3C82H. So stack pointer value is initialized as 3C82S. After that, there are 3 pop operations. 3 pop operation. In pop operation, address of the stack always increase by 2. By retrieving 2 byte of data from the stack, address of the stack pointer value always increases. Okay, so there are 3 pop operations, so stack pointer value will be increasing by 6. Okay, so you may just conclude here 3C82S adding 6 to this will be 3C88H. Okay, so see here, this is the starting value 3C82. Now retrieving 2 byte data in PSW, it will decrease by 2, 3C84. Again retrieving push pop H, it will decrease by 2 raised to 3C86. Again this is the push HL and BC. Okay, so first PSW, HL and BC. Okay, so 3 operation 3C82, it will reach 3C88. Now return is nothing but pop and call. What will be the pop? Pop will be the what was the initially stored next instruction, 1006. So 1006 again will be retrieved from the stack. 1006 will be retrieved from the stack. So again stack pointer value will increase by 2. So then 3C882 it becomes 3C8A. So answer will be SP will be 3C8A. This will be our answer. Okay. Now let's do another program. Here it is written main program is 1002 move B comma C, 1003 call 5985S, 1006 MVI D29, and subroutine program is written as 5985 MVI 00S, 5987 call subroutine 1. Subroutine 1 contains INR, A and return. Okay, so subroutine 1 is basically subroutine 1's address is given here, 598A. Okay, so it is asking what is the content of the accumulator. So let's do this. Move B comma C, content of C will be moved to the B, calling 5985H. Before calling we need to start this address into the stack. Okay, so stack pointer value whatever will be the stack pointer value, it will decrease by 2 after storing 1006. So stack pointer value decrease by 2. Again, now subroutine instruction 5985H contains MUI A00H. So 00H will be moved into A. The content of A will be 00H. Okay, then calling subroutine 1, and subroutine contains 598A. What is the address of the subroutine? 598A. 598A will contain INR A. So increment the accumulator by 1. So it will be incremented by 1 from 00 to 01H. Okay. Then a return to the main program. Then returning to the main program again. Here is the program pointer value. Increment A 1006. Okay, let's check here. Program counter value 1006 SP minus 2, and here again calling subroutine 1. Calling subroutine 1, the address of the next instruction again will be stored in the stack because this is the call instruction. So address of the next instruction will be stored in the stack, and again stack pointer value will decrease by 2. So we store 598A and stack pointer value decrease by 2 from SP minus 2 to SP minus 4. Okay. And stack pointer value 598A. Now it is a return instruction. Return instruction again it will go to main program after retrieving the address 1006. So again this instruction will come back to the main program, and A will be incremented by 1. So final value will be A02H. Okay. Now third and last instruction of the branching operation is restart instruction. What is it? Is just like a 1 byte call instruction. It is used when execution straps into interrupt. That's why it is called the software interrupts. it is used when the execution traps in interrupt. Execution is trapped in the interrupts. RST no operand, IWS will be 1 byte. N can range from 0 to 7. So how many software interrupts can be there? RST0, RST1, RST2, 3, 4, 5, 6, 7. So there can be 8 software interrupts. When this instruction will execute, control will transfer at the specific vector location of memory page number 00s. So starting memory page number will be 00s. So for RST0 it will be 00h. Okay, so that means restart instruction will contain the vector location, and vector location can be calculated by multiplying. Suppose we have RST0, so 0 is multiplied by 8 and converted into hex. RST1, 1 is multiplied with the 8 and converting into hex. Okay, so we can see here RST0 vector location will be 0000h in 4 bit, in 4 digits, that is the hex numbers. RST0 will be, what will the hexadecimal address location? 0000h. RST1 will be 00008. So 1 into 8, that is 8. Okay, now 8 can be converted into hex, so it will remain 8, because 8 is less than 16, so 8 will be 8, no problem. Okay, now RST2, so 2 multiply 8 will be 16, and 16's hex will be 10. So RST2 becomes 0010h. Vector location of RST2 will be 0010h. RST3 can be calculated. 3 multiply 8 and converted into hex will be 18. 4 multiplied by 8 and converted into hex will be 20. Okay. Now addressing mode. Addressing mode for the software instruction always implicit addressing mode. Machine cycle. Machine cycle will be S. It is under the instructions crisp. Okay. Now there are some advanced arithmetic instructions. ADCR. IWS is 1 byte. R can be A, B, C, D, E, H, L and M. Okay, so content of R will get added in content of the accumulator. ADCR is, what about the instruction is that content of R will get added into accumulator, and the carry will be added at the LSB also, and the content of accumulator will be updated according to this operation. Age added with R plus carry, what was the previous carry will get added into the accumulator, and the result will be stored in the accumulator. Okay, so see here example. A is 21, 21h, B is 20, carry is 1. Okay, so ADC B content, so A is 21, B is 10, so it is 10, and carry is 1. So accumulator content will be addition of this. What will be? This is 1 0 0 1 0 0 1 1 0 0. This is the content of the calculator. Addressing mode. If R is not equal to M, it will be register addressing mode, and if R is equal to M, it will be indirect addressing mode. Similarly, machine cycles are not equal to M, it will be just fetch operation. If R is equal to M, it will be FR. Okay, we already studied this kind of instructions where M is included as a register address. Next instruction is ACI 8-bit data. Again, its IWS will be 2 byte, and operation will be like this. 8-bit data will get added in accumulator with carry. 8-bit data will be get added into accumulator with carry and result will be stored in the accumulator. Addressing mode of the ACI 8-bit data will be immediate addressing mode. Machine cycle will be fetch R. For ACI will be fetch and 8-bit data it will be R. So machine cycle becomes FR. Okay. Third instruction is SBBR. Okay. The IWS will be 1 byte. R can be A to M. Any of the register can be. Content of R will get subtracted from the content of accumulator with status of carry. Okay. So you have seen this instruction. ADCR, content of R will get added to A with carry, and here content of R will get subtracted from A with carry. Okay. So the operation will be like this: A minus R minus carry, and result will store in the accumulator. Again, coming to the addressing mode, R not equal to M, it will be the register addressing mode, and R equal to M, it will be indirect addressing mode. Machine cycle, if R is not equal to M, it will be just fetch operation, and if R equal to M, it will be FR. Okay, so this was the third instruction. Again, coming to the in advanced arithmetic instruction, SBI 8-bit data. Okay, so again you studied ACI 8-bit data, so similar instruction will be in subtraction SBI 8-bit data. Okay, so accumulator 8-bit data will be subtracted from the accumulator, and carry will also be subtracted, and result will be stored in the accumulator. So see this operation. Okay, machine cycle will be fetch and R, immediate addressing mode. Okay. Now instructions related to the HL pair. So here first instruction related to HL pair is LHLD 16-bit address. Instruction word size will be 3 byte. Okay, and this instruction will execute data available at the memory location that is given in the last will load in the L, and the data available at the next memory location will load into H. Means data at the lower address will store in L, and data at the higher address will store in the H. So this is the load operation, the data transfer operation. So status of flag here also will not be affected. So 16 at the 16-bit address location, 16-bit address location mentioned here, the data available at this 16-bit address location will be load in L, and the address location plus 1, 16-bit address location plus 1, data at the 16-bit address location plus 1 will store in the H. Okay, so see this operation. Data at the 16-bit address location will load into L, and data at next address location will store in the H. Okay, so see this example: LHLD 201CH. H will contain, this is the address location 201CH. So 201CH, this 201CH contains 69H, and next address location 201DH contains 78B. Okay, so 20CH will be loaded in L. What is the data? 69H will be loaded into L, and the data from the next address location will load into H. What is the data? 78B. Okay. Machine cycle will be, what will be machine cycle? Machine cycle you may see here. For this will be fetch for 16-bit address will be RR, F, R, R. Okay, and again reading one byte data from this address location and 1 byte data from this address location. So for LHLD, machine cycle fetch, reading 16-bit address location, the machine cycle will be RR, and reading data from two address locations again will be RR. So machine cycle will be FRR for address reading the addresses, and RR for reading the data. Okay. SHLD it is 16-bit SHLD 16-bit address. Instruction word size is 3 byte. Okay, so store whatever the data at the 16-bit address location into store the data from L to 16-bit address location, and data from S to next address location, that is 16-bit address plus 1. Okay, so this operation is just opposite to the LHLD 16-bit address location. In LHLD 16-bit address location, we are loading H and L from 16-bit address and next 16-bit address, and here we are storing the data from H and L to the 16-bit address location and next 16-bit address location. So data of the L will be loaded into the 16-bit address mentioned in the instruction, and data from H will be loaded into the higher address 16-bit address plus 1 here. So L will be moved to the 16-bit address whatever is mentioned here, and content of H will be loaded to the next address location, that is 16-bit address plus 1. So machine cycle will be FRR for this FRR. Okay, and data of the content of the L will be loaded into this. So write operation, again write operation, so FRR WW. There not be 3W, only 2W. Okay, FRR WW, FRR WW. Okay, so next is the exchange no operator, XCHG no operand. Instruction word size is 1 byte. When this instruction will execute content of DE region exchange with the content of HL register pair. So this instruction is used to exchange the data of the DE with HL. Okay, so content of E will be exchanged with L and content of H will be exchanged with D. Addressing mode will be implicit addressing mode and register addressing mode. Machine cycle will be fetch, that because there is no operand. Next instruction is XTHL. Again it has no operand, IWS will be 1 byte. The operation, when this instruction will execute, content of HL pair will exchange from top of the stack. Okay, so XTHL is just the push and pop operation. First push, store into the stack, and then pop, and when you are popping the data from the stack, it will be stored into HL pair. Okay, so from the top address it will go to into from the top address of the stack it will go into L, and from next higher address of the stack pointer will go into L. So again machine cycle will be FWWRR. Okay, so why machine cycle will be FWWRR? Fetch for the XTHL, and first for push operation it will take 2W. Okay, and for pop operation it will take 2 hours. Okay, so machine cycle will be F for XTHL, and for push operation it will be W, and for pop operation it will be R. So machine cycle will be FWWRR. Okay, addressing mode implicit, register, and indirect addressing mode. So you have to remember these are the special instructions which use multiple addressing modes. Next instruction, SPHL no operand. Okay, so SPHL and PCHL, you may remember how many machine cycles? 6T machine cycle, 6T states, or S machine cycle is S, SPHL and PCHL. Okay, so here SPHL, no operand, instruction word size will be 1 byte. When this instruction will execute, content of HL pair will copy in stack pointer. Okay, so you may see here the name itself specify the content of HL will store into stack pointer, top of the stack pointer. Okay, so just moving the content of H and L into stack pointer, so it will be as a data or will be the address, it will the address of the stack. Content of HL will be stored into stack pointer, so stack pointer will be initialized, or stack memory will be defined into main memory, where the top address of the stack will be the just content of the HL pair. This instruction also used for initializing the stack indirectly. Okay, so in indirect mode, stack pointer is initialized by the instruction called SPHL. Okay, now PCHL, what this instruction is specified? This instruction specifies that content of HL pair will be copied into the program counter value. So program counter value can be initialized with the H and L pair. So we can say this instruction is used to indirectly specify the program counter value. Okay. So again, addressing mode, remember implicit and registered addressing mode, machine cycle will be S. Okay. So all these instructions we studied are data transfer instructions. So status of flag will not be affected. Okay. So we stop here and we'll come to the next lecture.